It's a couple of minutes after 10. So welcome all of you to this webinar on environmental impact efficient aluminium recycling. And this is the 40th of our webinars, so we are really happy for that. We are a bit celebrating, I guess. We have, as usual, we have a good spread from different countries. We have, I think it was like 14 countries today with us and 37 who signed up. You are so welcome, all of you. You will soon meet these guys, the presenters. Special welcome to Benjamin Brash from Stena Aluminium and Professor Anders Jarfors. You will introduce yourselves later. Me and Stefan will be your webinar moderators from the webinar management team. And after this short introduction, we will have presentations and then, as usual, a panel discussion. And of course, we would like you to join in and discuss and challenge the presenters with tough questions. We will wrap up 11:30. And if you haven't been here before, this was once the Webland project, where we had a lot of participants from many countries in different topics, and it was so successful. So we think this is a really good platform to spread new research. So we will continue with this from after the project. Please have your microphone turned off. And of course, as I said before, engage in the chat and panel discussion. You will have the recorded webinar after, and the discussions will not be recorded. Probably you know all this already, but you have the buttons here for mute and start video if you want to say something, and the chat function. Okay, I think that is absolutely the last slide before I hand over to Benjamin. The floor is yours.
Thank you very much. I will share my screen. Okay, like that. So I believe you can see my screen and you can hear me properly now, I hope. Great, okay. So thank you, Madeleine, for letting me present here at this webinar. Short introduction about myself. So Benjamin Brash, working as a technical sales specialist for Stena Aluminium, and I've been with Stena Aluminium roughly 2 years now. My background is in metallurgy, so I've been previous to Stena, I was at Profilgruppen for 2 years. So that was also aluminium, but extrusion and not casting like it is today. Previous to that, I was a couple of years at Höganäs working with metal powders in the south or southern part of Sweden as well. So today I will give a presentation about the title is The Role of Silicon on Greenhouse Gas Emissions. We look at the current status and also have some look at the future as well and have a future look. So the agenda today, I think quite a short agenda, but we will have a background, of course, looking at both very briefly into Stena Aluminium, what we do, and also the general kind of smelting process of aluminium and the recycling process of aluminium. We will look at the greenhouse gas emissions during the smelting process and what is contributing to those greenhouse gas emissions. And we will have a future outlook as well. So first heading into the background then. So very briefly about Stena Aluminium. So where Stena Aluminium is situated now in Älmhult, kind of southern part of Sweden, it's old industrial grounds, you could say. So there's been business here for a long time. Founded already back in 1906. Back then it was not aluminium, it was other types of recycling of textiles and other materials, but been doing aluminium since 1949, so also quite for a long time. It has not been owned by Stena during this whole time. Stena came into ownership roughly 20 years ago. And of course, part of this Stena sphere or the Stena group. So that's also consisting of Stena Recycling, which I think many of you are familiar with, but also Stena Line. So the ferries is also part of the same group or the Stena sphere. The Stena Aluminium has roughly 100 employees, only one production site, and here in Älmhult, and that's where almost everybody is situated as well. What do? We do scrap-based production of ingots, ingots which we supply to mainly foundries for high-pressure die casting, but also sand and permanent mold casting. We have an annual capacity of around 70,000 tons, looking to increase this, of course, in the upcoming years here. We have a permit allowing 90,000 tons annually. Currently at 0.63 kilograms of CO2 equivalents per kilogram produced aluminium. And we will, of course, go much deeper into that figure in the upcoming slides here. But that's the average value for the whole production. So looking very briefly into the recycling and smelting process and the process flow, it starts with a raw material, of course, and that is scrap. And it can be many types of different scrap. So basically, all you can think of that is made out of aluminium, you can also find in our scrapyard. So a lot of different materials. Some materials go through a pressing operation where we press the material into packages. That's just to increase the bulk density of the material. We also have ships, machining ships, and they need to go through a briquetting step before they go into the smelting furnace. These smelting furnaces can look a bit different depending on the recycling plant, of course, or the smelting plant. We have a rotary tilting furnace, or we have two rotary tilting furnaces. Some smelting or recycling plants, they have reverberatory furnaces, and there are other types of furnaces, of course, as well. So two of those rotary tilting furnaces, once the material is melted down, we can then transfer the material to the alloying furnace. And in the alloying furnace, we, of course, add the alloying elements. We then supply material, as I said, ingots. So we do casting of ingots. We also have liquid delivery in ladles, and that is also the reason for why doing a liquid delivery is also to reduce the greenhouse gas emissions. And it's something that we have, and also some of our competitors down into looking Germany, Poland. It's quite also common to have these kind of liquid deliveries as well. So if we look into the raw material a bit more in detail, so this is just 4 examples of how it might look. As I said, there's a lot of different types of scrap that we use, and it's basically anything that can be in aluminium, we use it. So to your left here is the typical kind of fragmented scrap, quite large volumes, and this is basically automobile scrap, which is shredded or fragmented, and then all of these different metals and materials are separated, and this is done through sedimentation, float and sink, by using eddy currents, magnetism, and different types of techniques to separate all the different materials. And at the end, you end up with one aluminium flow or several aluminium types or scraps, and other metals as well. And we, of course, purchase then the aluminium part of that scrap. And I should say also that we do not do so much sorting at our facility. We purchase the material, and then it's usually already sorted into different fractions. We purchase the main proportion of our material from Stena Recycling, so it's in the group. Another type of material, wheels, quite highly sought after in the market, I would say. Quite homogeneous since it's mainly one alloy, so but it was also a good source of material. Ships, as I mentioned, we use also quite a lot of the ships. These are ships for machining, so of course you machine both profiles, but also a lot of the cast materials is sometimes machined, and then you get ships, and you need to recycle that as well, so that we use in our smelting furnace as well. And this is what I mentioned that we do the briquetting of as well to increase the yield during the smelting process. Also some rolled products we use, and it can be profiles as well, and so on. So it's quite a broad base of materials that is used. So looking more into detail of the alloying step, we need to do alloying, as I mentioned, and it depends, of course, on what the customer wants, the alloy spec that the customer wants. Also depends on the scrap mix that you use, of course, because in the scrap mix you start with an alloy composition or a scrap composition, and then you need to often add some alloying elements, and it will depend then both, of course, on what the customer wants and your base kind of scrap composition as well. We do mainly alloys for casting. So as I said, high pressure die casting is the main proportion, but also permanent mold and sand casting supplying to foundries. And there you have quite high silicon contents. So usually it's in the range of 7 to 12%, I would say. So quite a lot of silicon. And silicon is also the alloying element that we add in the largest quantities, of course, then. Why do you need silicon? Well, during the casting process, you need silicon because you need to have the fluidity and the castability throughout your mold during your casting process. So that's why you need these silicon contents. So looking a bit more then into detail of the greenhouse gas emissions during the recycling and smelting process. I should say that we have calculated here according to the greenhouse gas protocol, and I know that this is quite a tricky field, maybe to how to say it, but there's a lot of different ways of calculating here, and there's a lot of some different standards and different ways of doing this. But we have chosen the greenhouse gas protocol to calculate our emissions. So looking into details here. A lot of figures on this slide. I will not go through all of this. But what we have done here is that we have looked at our total emissions during 1 year. So it's both from 2019 and 2022. We will also are also in the process of updating this so that we will include, of course, 2023 years numbers as well. They are not, they're almost done, but I don't have them here, but we will have those soon as well. So what we have looked at here is the whole year and the annual then emissions and what is contributing to this the total emission. And this then includes scope 1, scope 2, and scope 3. And I believe that many of you are probably familiar with these terms, but scope 1 is the emissions in your plant or in your factory, between your gates. Scope 2 is kind of the energy needed in your plant. Scope 3 is emissions caused outside of your plant or your facility. So it's raw materials that you purchase, for instance. So if we look a bit more into detail, we see that scope 1, 25% of the total emissions. So it's quite substantial, and 25% here is the LPG. So we use LPG for the smelting furnaces and the alloying furnaces. And this is, of course, something that needs to be solved in the future, or replaced with some other type of fuel. And this is also quite an issue for the whole industry, I would say. A lot of course, facilities and production sites use LPG during the smelting process. Scope 2 is basically nothing. Scope 3, that's where we find the majority of the emissions, so it's 75%. And if we look more into detail, we see that it's actually 41% is actually silicon. So that's silicon that we add then in the alloying furnace to achieve those customer specs. So silicon is quite substantial when we look at the emissions. And where does those 41% stem from? As I said, this is scope 3 emissions, so they are not emissions which occur in our plant. It's during the production of the silicon. And I should say that we also use quite a green silicon. There's of course a variety here depending on where you source your silicon. But it's still quite substantial. And where does it come from? It's scope 3 emissions. So it's when you produce silicon, you start with quartz or silicon dioxide, and then you have to reduce this with a carbon source, and then you get silicon, but you also get carbon monoxide, carbon dioxide, and that causes the emissions then. There is also, of course, an energy consumption within this reduction process. I believe it's all usually electric arc furnaces, so there's also an energy consumption there, and that you can, of course, solve by using green energy, but the reduction process is a bit more tricky to solve. There's also an effect on the scope 1 emissions, because if we add more alloying elements and more silicon, we need to use more LPG during the alloying step in the alloying furnace. So there is actually also an effect on the scope 1 emissions, but I would say that of course substantial part is within the scope 3 emissions during the production of the silicon. But anyway, when we calculate the total, we get a figure of 0.63 CO2 equivalent per kilogram produced aluminium. So it's of course fairly low, and I think usually when you look at these figures from recycling smelting facilities, they are usually somewhere in that range between 0.5 and 1, I would say. I should say also that this is then scope 1, 2, and 3, as I mentioned, but we are excluding the downstream activities. That is mainly because we don't know exactly our customers' emissions. Sometimes we know, sometimes it's difficult for them to tell us. So that's why we have kind of said that you have to add the customers' emissions on top of our emissions if you want to look at the whole chain. So what we have also looked at is the difference between different alloys. As I said, we've supplied foundry alloys, but there's a lot of different foundry alloys, of course. So it's interesting for the customer and also for us, of course, to know what is the recycled proportion in the different alloys. So here we have listed a couple of different alloys and alloy groups. So basically it goes from the copper silicon alloys, that's for instance the 46,000 alloy. That is, I would say, the most common foundry alloy today. And there you have a 96% recycled content, meaning that it's 4% primary alloying elements that you need to add, or that we add in when we produce this on average then. And then it goes down in the lower copper content containing alloys. So this half silicon is, for instance, the 47,100, it's 93%. So the recycled rate goes down a bit. So here we have to add a bit more of the primary alloying elements. And it's the same 93% figure for instance, the 44,300 alloy, which is also quite common. We have also recently developed these Rio alloys, and there's a slide that we have a bit more details about the Rio alloys. And there we have very high recycled content. So there basically we have to add very, very small amounts of primary alloying elements. So that's how it looks like when we look at the different alloying groups. This table also shows kind of the similar setup. So we have the different alloy groups here, going from the high copper containing alloy groups, 46,000 for instance, as I mentioned, and then going downwards to lower copper contents. And then we have added then the silicon content, and also we have looked at how much silicon are we adding on average to these alloying groups. And we have looked at how big are the emissions from the actual silicon additions. So here you see the silicon generated CO2 emissions, and as I said, it's lower for this 46,000 alloy with a bit higher copper content, and then it goes down into higher silicon additions and higher generated CO2 equivalents then. And then we have the other generated, and here we have not looked into detail. Of course, there will be some differences here with the other generated CO2 as well between the different alloying groups, but we believe that it should be minor differences between the alloying groups. And then you have the total as well, then the total CO2 impact of the different alloying groups, and the total is of course then the other plus the silicon generated emissions. And then if you look at the Rio alloys, as I mentioned, they are very low in silicon content, meaning that you have to add, of course, very little silicon. So it's very close to zero, meaning that they have the lowest total emissions. So what have we done, and what is possible to do to kind of reduce these alloying greenhouse gas emissions? Well, the first step is, of course, to kind of generate this kind of data to be able to make an informed decision for the customer, but also for our sake, of course, to know what are the emissions in the different alloying groups. So the generation of data is kind of the first step there. Scrap recipe optimization to reduce the need of alloying. When we produce, as I mentioned, we have a lot of different scrap types. So by choosing this wisely and combining correct type of scraps, we can try to get as close to the final alloying composition as possible when we choose these different scrap types. And this is, of course, something that we have worked with for a very long time, but always trying to improve as well and trying to get as close as possible to the final alloying composition. We were only using the scrap. As I mentioned, Rio alloys with low silicon additions. So these are alloys with, as it says here, 2 or 5% silicon final content. So it's very low, meaning that you don't have to add basically anything. It's very low amounts of additions. So that also means low total emissions. Circular material flows is, of course, something which is talked a lot about, and we are working with circular material flows as well, and these kind of closed loop solutions, and we're always looking for more of those kind of solutions as well. What is kind of important also to mention is that there is, of course, even though we are working with a lot of these closed loop solutions and circular material flows, there is kind of a supply and demand mismatch, obviously, here when we look at the silicon addition. So it's difficult to, for instance, produce 46,000 alloy with only 46,000 scrap. So there is always a bit of a mismatch, both in the compositions of the scrap and the compositions of the alloys, and also in the quantities of the different scrap types and alloy types that the customer wants. So just a short slide and some short information about the Rio alloys, since it's maybe not something that everybody is familiar with, but in short, Rio casting means it's a semi-solid casting process where you're actually using a slurry when you're casting, and this allows for a very low silicon content. As I mentioned, usually you go between 7 and 12%, but with the Rio casting, then it's possible to go much lower. So you can go from maybe 2 or even 2 or 3, 4, 5% silicon, and it's castable. So that means very low silicon additions needed for these products. So significantly reduced need of alloying, obviously, then. And at the moment, we have 2 Rio alloys that we have developed, and we are looking, of course, at developing more of those. And we have a Rio Cool, which is basically for thermal management. It's very low in a lot of the alloying elements, meaning high thermal management or good thermal properties. Rio Green is more of a replacement for the 46,000 alloys. It contains some copper. And this process has numerous advantages, of course. Well, 2 of those being an increased tool life, and also possible to cast with a reduced machine size. So there are economical benefits to the process as well as technical benefits. So short, also look at the future and what the future holds. So there's obviously a lot of aspects here if you look at what is affecting need of alloying. So of course the main one being supply of scrap. How much scrap is there available on the market, and what's the composition of those scrap sorts that are available on the market? One thing which affects this is the lifespan of products. I mean, aluminium is quite good in the sense that it's very durable, and if you look at the automotive sector, we have quite long lifetimes or lifespans of the product. But that also means that if you look at the automotive sector, for instance, you might have a lifetime of 15 years for a car. That means that the scrap from the automotive sector that is available today is actually the volume that was produced 13, 14, 15 years ago. The demand of products and alloys, of course, is important. What kind of alloys is it that the customer demands today, and what will they demand in the future? And I think Anders will talk much more in detail about this the demand question. Because it also obviously affects what kind of alloys and alloying additions that we need to do. The share of material being recycled, we have quite high recycling rates of aluminium, and it differs a bit if you look at different sectors. But can we increase this, then that would be good, of course. Legislation and policies as well. So what will happen in the future? Well, most likely there will be an increase in the supply of scrap. And that is kind of what these figures show here to your right as well. Increased circularity, which is talked about a lot. Will there be a reduced need of alloying? Yeah, it will depend, of course, on the kind of scrap which is available, and also what the alloys are actually requested by the customers. What we are definitely seeing already is that there will be more of a battle for the scrap in the future, since a lot of the primary producers are also switching over and looking at more secondary based products. So how will we go to a more increased circularity and an increased supply of scrap? It's a lot of things which are brought up in this kind of circular aluminium action plan from the European Aluminium Association. So circularity, of course, making it easier to identify materials when you recycle, easier disassembly. Improved collection and sorting is talked about a lot, meaning that you can separate these different scrap flows into more specific alloy grades. The export of scrap, there's some scrap being exported today. That will most likely change in the future, and keeping scrap more in Europe. Alloy development is also important, as I mentioned. Reocasting is one route, but also making more tolerant alloys, meaning that you can use kind of a broader scrap base as well. So just a couple of conclusions here. So significant proportion of the emissions during the recycling and smelting of aluminium stems from the primary alloying elements, as we have seen, and mainly silicon. The need for these primary alloying elements and the greenhouse gas emissions will obviously depend on the scrap that you use and then the alloy that you are producing, and we're seeing some differences between the different alloys. Realloys has been developed with the lowest greenhouse gas emissions, at least in our product portfolio. And we are kind of seeing an increase in the share of recycled material and recycled production within the upcoming years, at least according to these predictions. Okay, so I think I am right on time now, 10:30. So that was my last slide. So thank you very much for listening to me, and I will leave the floor now to Anders.
Thank you very much, Benjamin. That was a very, very interesting and very, very good talk, and it matches very well to what I'm going to talk about.
Thank you.
I presume that you can see my screen now, or at least very shortly.
Yes.
You can see it perfect. Yes. So I will sort of present a work that we've been doing here at Jönköping University, and I've been doing that together with my colleagues Tony Bogdanoff and Lucia Latanzi. And the topic is functionally integrated castings for body in white applications and the consequences for material use and mix in automotive manufacturing. So what I'm actually going to cover in this talk is a little bit about the review of the aluminium usage in the automotive industry, and thinking about Benjamin's presentation and the scrap sorts that were shown in the beginning of Benjamin's talk is the leftmost image, where you have sort of the Zorba scrap being sorted into the aluminium fraction, and that first fraction, the automotive part, that is essentially the body in white and some other elements that will be well, ending up in that pile. And what we will do is take a look at that portion of the material and look at what are the consequences for the electrification and what are the consequences for the use of mega casting, because there are a change in the material usage. And as Benjamin said, there is we have a scrap mix today, and what will be needed in now and forward is different. And what will be returned is something which is also slightly different. So we are looking at the automotive sector and that portion of the material flow, so to say, and we're taking a global perspective. And looking in Sweden, we have rather large efforts in this activity. So there are new foundries being set up with an annual requirement in the order of 55,000 tons per year. So it's a rather sizable effect and consequence from the automotive industry on the material circulation. So I will take a little bit look at aluminium alloying elements. We'll talk about the use trends in the industry. We'll talk about the automotive market as it's, and also scrap. And I will go through the results in a closed loop scenario where we're looking at the feedback loop of the scrap and the projected future demands based on the market type of analysis, and then some conclusions. But foremost, what we know now is that we have as a greenhouse emission, and that's the graph to the right here. I will just bring out my pointer here. So we are about 37 billion tons of annual carbon emission. And this number we should keep in mind based on what we will see as in particular as a consequence for the alloying additions in the form of silicon. Because as Benjamin said, silicon is really a major carbon footprint generator in the automotive industry. Now, when we're looking at the use of aluminium, of course, we have design-driven matters. So you have the first part here where you need to rethink, refuse, and reduce. And in the design here, there is a rather large change taking place in the automotive industry with the use of mega casting. Electrification also changes the first part here on what type of alloys we are actually using. When we have reused, repair, refurb, remanufacture, and repurpose, these are essentially also in the use phase of the material, and that does not strongly affect the material cycle in the automotive industry. But what comes back here in the end is actually the recycling and the recovery part of materials and such. So the material flux are primarily driven by the design and the changes in the structure of the automotive industry and the type of cars that we use. And then the recycling here, that is how we can balance the new alloy compositions of the cars and what we actually have in the feedback loop. And just to make some small remarks on silicon, this is, you recognize this one, this is not the updated material that Benjamin showed, but it is still a very strong effect from the purchased raw materials and from the silicon. And the problem of silicon, it is not only based on the greenhouse gas emissions, it's also the embodied energies that are being part of, so to say, a built-in issue in the automotive industry. Because if you look at the heat of fusion of the material, we have all the elements in the periodic table down here. Aluminium is slightly higher than most of the materials. Then we have beryllium and silicon lies here, and then we have the outliers with carbon and boron here. But silicon is really an exception here. It has a very high energy of melting, and this is reflecting what Benjamin said in that it has an effect on the LPG usage. And by choosing high silicon alloyed materials, you build in an energy hysteresis in the recycling. So every loop you recycle the material, it takes more energy. And if you look at the different alloys, you have the international materials or American standards with A380, A383, A384. So if you take the Neumann rule, just by rule of mixtures, you get very high. And of course, there are some entropy effects. So if you take thermal data, it's slightly lower here. And if you take the real cool alloy that was mentioned, it's significantly lower, and the real green is also lower. And what we know that in mega casting, there is also an alloy change. So you will not use these A380 type of materials for most of the large body in white materials, but it will be something more like the Tesla alloy with slightly lower silicon contents and a different structure, so to say. So the Tesla alloy here is represented here. It also has a slightly lower energy content, but we can do better in alloy development. So now looking at the automotive industry, there are some changes, and we know that electrification is definitely one of those. And when we look at this is from an analysis from Polestar, where you have a benchmark of the Volvo XC40, and then you have a number of Polestar cars, and we have a different energy scenarios. You have petrol cars, we have global electricity, the European Union electricity, and then a fully green alternative with wind and energy. That so for a petrol car, you see that the majority of the energy is within the use phase. And then if we go to electrical vehicles, you have an increase in the material usage. So this is essentially the battery, a little bit also on other material usage. And then the better energy mix you have, the better the overall footprint is. So with a completely green solution, we have about 50% reduction of the actual greenhouse gas emissions, of the carbon equivalent footprint. But this portion here, as Benjamin said, it depends a little bit on your material reduction sources. You take silicon, you have a carbothermic reduction process, which is quite common. And that is sort of built in here. So this portion, in order to reach zero or a significant reduction in the manufacturing side, the actual alloy selections and the type of materials we use and our ability to reduce the energy in the recycling part and use of recycled material will affect this part here. And this is a little bit where well, electrification sort of takes care of this orange part, but it might be affected based on the ability to deal with the lower part from the manufacturing process selections. And we should remember also that this transition should also be made not only a reduction of carbon footprint, but it should also be economically viable. So it should mean that it also should provide work opportunities and good market opportunities. And this is where the mega casting and giga casting parts comes into play. So one part is the material number reduction. So if you take the rear floor of a car, it's typically 100 parts today, and you can reduce that into one single casting. And this means that you sort of have 15 to 20 material number reduction. So you have 15 to 20 materials being made into one casting. And this is also where we can talk about the recyclability of the product. So having a material number reduction is an end of life increase. So end of life is easier if you can reduce the number of materials, and that means that you get a better scrap to recycle and such. And then when you look at the operating and capital expenditure changes, if you think about the space requirement, you instead of having all these assembly lines, your body shop is reduced in a footprint by 40%, and this is reported for Tesla by JP Morgan. Equipment reduction, you have less joining processes. So somewhere between 1,400 and 3,000 welds are being reduced, so reduction of 300 robots. Production time goes faster because the logistics of handling all these 100 parts into different sub-assembly stations is quite difficult, and that includes handling, assembly, fixturing, and all these bits. And overall, you have a significant cost reduction also by typically 40%. So this is the driver to look at. You have electrification as the first part, and then we need to look beyond electrification. And that's where mega casting comes into play. So taking a little bit of a look at this, we can see the market projections. So if we start with the number of cars being produced per year, the blue line here with the economic crisis in 2008 and 9, and then we have the COVID effects here. But it's sort of growing in some kind of direction. So if you take a upper bound estimate, we can see that the number of cars would continue to grow. And in 2060, we would be passing well over 150 million cars per year in production. We may argue if that is reasonable or not. So what we do is that we also take a step here to see if we can have a lower bound estimate. So we have a low growth. And this is essentially taking this growth and taking it, weighted with the lifespan of the cars. So when we look at the average worldwide lifespan of a car, it's about just over 10 years, and then it's growing like this, and it seems to have a linear growth. I know that the Swedish cars typically live longer, but there are a lot of cars on many different places in the world. But this is roughly how we do that. So we start from 22 and we normalize the lifespan here. And that's how we reach these two different levels. Now, the thing that has also happened, and we may argue if this is also reasonable, but we have a weight of the cars that are constantly increasing. That is essentially all the passive safety. There may, of course, be a break in here as well, because the more electrified the cars becomes, the more they will be talking to each other, and that might be an active safety component that might break this passive safety growth. But looking at the car weight, assuming that it's sort of growing a little bit, and we know that the electric vehicles are also much heavier, so it's not an unreasonable projection here. Now, the aluminium content in the car is also increasing, and this is in percentage, so that we have numbers on the average aluminium content in cars, and of course there are large variations between different brands and such, but this is sort of the average aluminium content in cars today, and it's growing quite rapidly. Then we have the electric vehicles, and this is battery electric vehicles that we are looking at, and of course they will expand. And what we've been looking at is this part of growth of the market penetration of this. And we take the logistic regression equation here and sort of see how it goes. And it seems as it's growing right now, we would have in 2037, 50% of electric vehicles in the world, which is not an unreasonable number, I think. They provided that all countries sort of join the race here with electric vehicles. And then somewhere towards 2060, we should be quite close to a fully electrified fleet, provided that this is what goes on in the world. Now, the big question is then also, when we look at this first scrap pile that Benjamin showed, what does that consist of? And that depends naturally on what type of production scenario we have. So today, if you take the internal combustion engines, the scrap pile that comes back contains about 5% silicon, 0.5% iron, 0.7% copper, a little bit manganese, a little bit magnesium, and some zinc, of course. So that's essentially what comes back from the car. And if you think about this, you have 5% in the scrap that comes back as a Zorba scrap, and then you try to make a casting alloy of that. So you need to go from 5% silicon to 7 or 8 or 9 or 10 or 11 or 12% silicon. So that is quite a hefty addition that you need to make. Now, this is changing dramatically when you take the electric vehicle, because it's much more sheet metal and extrusions in that. So the silicon content drops in the electric vehicles that are being produced today. So you end up with a material that only requires 1.38% silicon. And then you have less iron, you have less copper, you have less manganese, you have a little bit more magnesium, and a little bit less zinc in that. Now, the thing that happens when you do the mega casting is, of course, that the mega casting cannot utilize these low values of silicon to have an average content of the car. If you add on the rear floors, you end up with about 3.5% silicon in the scrap that comes back. And of course, this is, it's not in press anymore. It's actually published in Resources Conservation and Recycling, work by Anton Rolseth and myself, and also with Polestar and Rice as participants in that paper. So there is different scenarios. So we have today's scenario, we have the electric vehicle scenario, and we have the electric vehicle with a giga casting scenario. So if we take that and we have the two different market projections, one which is, so to say, lifespan compensated, and one which is not. So just continued mad growth or the lifespan compensated. So taking a material balance, and we look at the aluminium needs, and I should say here that this is not carbon emissions, this is the supply of aluminium from the scrap minus the demand from the amount being used in the cars. And now this is taking the lifespan of the cars into account. So the scrap that comes back today is the scrap that was, sort of say, depending on the lifespan of the car. So that's the part behind that. And you can see, if you look at the overall scale, it's not that much of a difference in the aluminium. It's a little bit of a change here. If we sort of say blow up this region here, we look at around 2030 here. So you need less, or you need it's a bigger gap between the supply and demand from the scrap if you use the electric vehicles. A little bit less with the mega casting, and then for the internal combustion engines, it's even a little bit less there. But it is on par, not that big a difference. And this is where you have the linear growth. If we now look at the growth with lifespan compensated demand, you can see that there's a little bit of a knee point here at 2022 when we start to do that projection. So we see that it's also growing, and the scenario is roughly the same. It's just that the absolute numbers are changing because of the volumes of the market is different. Now, so this is not surprise. We need always to add aluminium to this. So either you buy secondary aluminium and you add that as a dilution, or you buy virgin aluminium and you add that, depending on how the actual market or the actual component will be produced, so to say. But there will always be a gap and a need for new aluminium to entering the system anyway. It needs to be taken from other sources than the automotive scrap. That is what I'm saying here. So now taking another look at the combustion engines and all the alloying elements. So the ones that we have thinking about is silicon, iron, copper, zinc, manganese, and magnesium. And with an internal combustion engine, of course, there is a constant need. There is no change in the composition of the material. So we see that it's growing. And if we blow up this part, it is a significant requirement on these elements, and it's continuously growing. And the scenario does not really change when we do lifespan compensated material. You can see that, especially for silicon here, there's a small visible knee here, and that is based on the change. So if you then blow up a portion here, you can see that it's all of them are now lack. So we will have to add all these elements. There is no time where it goes above this line, where the scrap actually supplies more alloying elements than what we need in our alloys. So there's a constant need for alloys if we continue with the combustion engine. So now the consequence is, now if we take the electric vehicles with the very low silicon content, that means that the scrap coming back from the old cars, the silicon will turn, and it's about 2030 sometime, and it will start to go up, and there will be a surplus of silicon. Now, if we look a little bit more in detail here, we can see here that the first material that will be coming in excess is the magnesium. And then we have manganese, and there is also iron and so forth, with copper being the last one. And there's a dramatic change here. So somewhere about 2045 or something like that, you pass also where you have a surplus of silicon, which then would affect the carbon footprint. Because then if you can match your alloys, which is one of the challenges that Benjamin mentioned, if you can match your alloys, you would actually have enough alloying elements in the scrap coming back. So you would only have to work with that mix and then being able to just add the aluminium in nice proportions. But that requires that we have enough understanding of what actually comes, how it's being sorted, and what we can achieve with that mix that we have coming in. So how good we are in using the scrap in the mixture. And that is, of course, now, since this is, we can take the next step also. This is also when you reduce the requirement of the cars. So the lifespan compensated part, and it's essentially the same. The scenario is the same, but the drama in the transitions is not as big because the volumes are less. So now being able to use the scrap, now the electric vehicle is quite a lot of sheet metals and extrusions right now, and that is a challenge when you do recycling. So the ability to match is much more difficult when you do raw materials, because of the manufacturing processes and such. They are much more sensitive to variations in chemistry. So therefore, if you think about the actual matching and the ability to do something, the addition of mega casting would make this transition a little bit easier, because the casting processes are more forgiving when it comes to alloy variations, and are not as well. The productivity in the process is not as sensitive as an extrusion process or a rolling process would be. Now, taking the mega casting into account, the scenario is the same. There's a little bit of a difference, because the balance and the feedback of silicon will be higher also further down the stream, because you have more scrap with higher silicon contents. But it's essentially a similar scenario, that starting with magnesium, and then you have manganese and silicon and iron sort of transitioning here, where you will have an excess of that. And the alloying elements that you would have further down is zinc and copper foremost, will be the last one to sort of transition into a surplus. So that will tell a little bit about what type of alloying elements we will have. And if you reduce the growth of the cars, it's similar, because the actual way that things are changing is not as dramatic. And you can see that there's a little bit of plus just around 2040 sometime, where you have all the changes taking place. Now, all these things have consequences. So if you turn back to the problem of silicon, the amount of carbon emissions in megatons that the embodied carbon footprint of virgin silicon has, which is 10.9 kilos per kilo of silicon, you take that and you look at the overall amount of silicon that is being added, that will correspond to this curve if you have the internal combustion engine scenario. And if you look at today, it's 439 megatons of carbon dioxide. And that corresponds to just about 1% of the global total emissions. So I would say that this is a rather significant number. So with the continued growth of the cars, you can see that the electric vehicles will change. And this is it will sort of reduce. And then if you add on mega casting, because of the fact that you sort of come into a balance a little bit earlier, we will end up with this type of scenario here. So just before 2040, we will be able to sort of remove and change this. So these are the happy points here. And taking the slightly reduced market change, we can see that the amplitudes are lesser, but it is obviously possible to sort of come to this negative portion here. So there is a potential solution to the silicon problem in the automotive industry, and there is a potential to close the loop and having enough alloying elements to actually produce the cars using the scrap, at least on an overall balance. And well, in terms of conclusions, the general balance and the EV transition. So without the EV transition, we will just have a galloping carbon dioxide footprint, and we will have a galloping resource need. So if we now try to close the loop, it will be possible to close the loop with the electric vehicles. And the challenge is essentially to sort of be able to use the scrap to turn it into wrought products. If you take the mega casting effects, well, the mega casting effects that will, of course, generate also a positive supply balance for the elements. And there's a slightly different sequence with the mega casting compared to the wrought materials, where the balance for manganese and magnesium, well, magnesium is first in all cases, but the balance for manganese is slightly different. And the casting process is a little bit more forgiving. So if one wants to be able to close the loop, the mega casting offers an attractive way also to sort of close the loop here in that way. And this is my last slide. I will hand over to Madeleine, but I can still manage the slides if you want.